Okay, today we will be learning what does it mean the complexity and try to solve several simple problems on how to measure the complexity of the program. So why I talk about complexity in general. So suppose you have a problem, like an algorithm. How do you measure its running time? Typically you measure its running time in seconds. But however, when you take your program to another computer, it will take a different amount of time to run this program because like the machines are not equivalent and etc. But however, you want to know their kind of the approximate value of how fast the program should work. So for that, there is a notion of complexity. So we can, by the algorithm, we can say how fast it will work in terms of mathematics. And this will help us to approximate will the algorithm works in like reasonable time. So consider the very simple problem of finding the maximum. Suppose we are given an array of integers which are bigger than 0. So we say like int max equals to 0, and then we go for I equals from 1 to n, max equals max of max AI, and return max. So what does it mean complexity? Complexity means the number kind of in the high level. It means the number of instructions here in their kind of in assembly code. So yeah, I wanted to say that we work in the RAM. Does everybody knows what RAM is? What? Yeah, exactly. So we have we will consider like the simplest system, kind of theoretical system, that we have a large bunch of memory, and each operations like reads and writes costs 1. Read and write. So we have at the beginning, so we have int maximum equals to 0. So we created a variable and set it to 0. So this costs 1. Then, can you tell me? So let's unroll everything here. Like, because we want to calculate the complexity that depends on some input. So our input is n and the array a. Can you tell me what is exactly written here in instructions? Like what could you come up with? Like this line. What does it really mean? Let me change max to m to not confuse anybody. Okay, so let me answer then the question. So at first we have a variable and we load AI. So we load to the stack. So we have like the huge amount of memory which is already accessed, and also each processor has its own memory in which it works with. So we read AI. Then we run if okay, yeah, so we also we load in the local memory M. No, it's in local memory. It's already in local memory, so we don't care. And then we have if m less than equal to x, m set to x. Unfortunately, this is not everything. To be more precise, so like this is equivalent code here and here. So as you can see, it is already like this line was from our experience like 1 because it is one line, but however it is not exactly one line, it is several lines. So in this case it is 1 line, 2, 3. To be more precise, this if is also not there. There is no if in the instructions of the machine. So like typically it is there compare m and x, and then g and z jump could somewhere id, and here is id. Like and id m set mx. So it's kind of even more complicated here. So we read, then we compare m with x, which already loaded into our memory, the memory of the processor. Then we compare it like do they less or not, and then if it's not, we have a conditional jump here that if m is bigger than x, we jump here, otherwise we set m to x. Yeah.
I have some message from people in Zoom, and
okay.
Focus on the camera.
Oh, focus on the camera there is. Okay, great, thanks. I always forget to do that. I always forget to turn off the... No, it's turned off. I cannot do anything. The focus is turned off. It's on 0. It seems that everything is fine. I can... Like, what is exactly the problem?
They sent me the picture from Zoom, and it's so hard to read from the desk.
Really? Okay, let me do the following then. Like, I know the problem with the Zoom. I will do the following. I will set up the stream to Twitch so like everybody can see it. Because like this is... I think this should be much better afterwards. Sorry for that. Okay. So I will start the broadcast there. I will send you the link right now in the Telegram. It should work. Okay. Could they get there? the one who is in charge of Zoom chat. Does everybody succeed to get onto Twitch? So like you could still maintain Zoom into the back, into the back, so like you can answer questions through Zoom while looking on the Twitch. So like there will be. Let me turn off the mic for Zoom. Sorry, I poorly hear you. Okay, so like now there shouldn't be any problems with. Okay, great. So you will have a delay of 10 seconds, but I will wait for it if you don't mind. So I hope that would be better. If you don't want, you can ask in Twitch chat, and I will try to answer. Okay, great. Okay, can you tell me what's hidden in 4? Can you propose how the 4 is really written?
Is compare a counter and jump to the beginning until the counter.
Yeah,
0.
exactly. It is that. So we have a counter I here, which is equals to 0. Then each time it is incremented inc I and compare against n and I. And if nothing happens, we jump here. So as you can see, how many iterations there is. So how many operations when their length is n? There will be 1, 2, 3, 4, 5, 6, 7. 7 operations for each element, so it will be 7n plus 2. Okay, so we know their approximate complexity in the number of instructions. Of course, this depends on the machine. Their exact number of instructions can be bigger or smaller, but the main feature of their complexity is that we forget about the constant. That's we start with, and for that, what we do, we introduce a notion O of f of n. What does it mean? O of f of like g of n is O of f of n if there exists n0 and there exists constant c such that g of n is less than c times f of n for n bigger than n0. What does it mean? It means that, like, starting from some point, the function, the gn, is less than constant, some constant times their times this function. So I claim that 7n plus 2 is O of n. So here is a little exercise. Can you tell me which c and n0 we could take? So we want to prove that 7n plus 2 equals to O of n. For that we have to find n0 and c, starting from which 7n plus 2 less than or equal than c times n. So what are your suggestions? someone in the chat can, someone who is online can tell what's there. Okay, any ideas? It's pretty simple. I don't understand what's holding you.
Do we have to find the minimum or any?
No, any. Like their definition of the complexity of big O is any. Like there exists n of 0 and some constant c such that this holds. So which c and 0 we can take?
For example, we could take 9 as c and
Okay.
1 as n.
Yes, that's exactly. So like let's give a little bit proof for that. So we want to prove that 7n plus 2 less than 9n, and then we want to compare, like if you subtract 7n from both parts, you will have like 2 less than 2n, and which is true for all n greater than 1. So okay, we proved that 7n plus 2 is O of n. Okay, great. And that is the main idea behind complexity. We don't care exactly how many operations there, as long as there is a constant that hides it. So we could have like so we have here previously, right? We have here m equals max m ai. We know that it happens to be a lot of different operations in the registers. But however, it is still some, like we know that this guy is still some constant number of operations here. So as long as we know that the constant number of operations there, we can calculate only the number of such operations here, and we know that it is linear. So we can simply say that it is O of n. So that's the main thing behind complexity, and it doesn't matter even on which machine you are running the code, what its speed, etc. We know this is the property of the algorithm itself. Okay, so also there are several other notions that exist. For example, there is omega of n. Omega of f of n. This means that g of n is omega of f of n if there exists n0 and c such that g of n bigger than c. Gn. We say that the algorithm is omega of f of n if it works not faster than f of n. So it cannot be run faster. And there is another final notion. So you can see that O of n tells you that it is it runs faster than f of n. Here it runs slower than f of n, and there is a notion theta, f of n. This means that there exists two constants such that it lies in O and in omega. So this part tells that it is O, big O, and this part tells that it's omega. Okay. Let's try to talk a little bit about their how to merge the complexity together. Suppose we have like O of f of n plus O of g of n. Like it is O of f n plus g of n. Is it clear that if the function if the function is all like we know that the first function is O of f of n and the second function is O of g of n, then their sum is O of f of n plus g of n. Okay, so I hope this is clear, and take their question here. Suppose we have O of n, and then we have O of n again, and then we have O of n again, and etc., and we have O of f of n times. And I do as this tells me. Okay, so this is O of n. Thus, adding this is also O of n. While adding the next is also O of n, and so on, and I claim that this is O of n. Where I'm mistaken. You add n 2 times, because when you add n 2 times, you would expect to get n squared, right? But using this kind of lemma, we could claim that the sum n times you sum O of n and it gets O of n. Where is their problem in mind?
Maybe those constants n0 and c would be different for different parts of the...
Okay, that would be different, and why it is the problem? Here they also could be different, right? But still it is clear that it is the sum. Okay, so how would we prove this? We would prove that this guy is less than C1 times f of n, this guy is less than C2 times g of n, and this guy then less than maximum of C1, C2, f of n plus g of n. Okay, that's clear, I think. The proof for this line. However, like it doesn't work here. Where I did a mistake here. So like suppose that so I claim that this is true. Okay? But this is less than C1 times n, this is less than C2 times n, and this means that what is the constant for the right part?
C1 plus C2.
C1 plus C2, yeah, exactly. C1 plus C2 of n. Great. So, as you can see here, if we will have like less than C1 times n, less than C2 times n, etc., less than Cn times n, Cn times n, you could see that this is exactly not O of n. I kind of throw away this constant. So like it's constant when you add this constant amount of time, but when you add it like linear amount of time, you will have here like this is C1 plus C2 plus Cn times n. And here it is. Here is this. This guy is not constant anymore.
Equal n.
Yeah, there are n of them. Yeah, so it is n squared to be more precise. Okay? So that's the trick. So you never should do this. You like when you add the constant number of terms, like you're fine. But as long as you add more terms, then it becomes complicated. Okay. Let's continue. So we talk about like the notion of complexity, but let's think about let's talk about how to calculate complexity on its own. So suppose that I will get a very strange function which is given n and it do while I less than n I equals I times 2. So can you tell me the complexity of this algorithm?
It should be linear.
Why it should be linear?
Because we do it n times.
Not exactly. We multiply I 2 times. Here is not like, okay, so let me write the similar algorithm. So there is a difference between these two algorithms. Here I have a plus, and here I have a multiplication.
Oh, okay.
So how many iterations do we have here of this of this loop?
N iterations. And
To be more precise, yeah, n by 2. Yeah, I understand that this is all fn. I agree with you.
okay, yes.
I agree, but this is like the number of iterations is n over 2. Like not exactly like n minus 1 over 2. Okay. So what's happening here? Each time we multiply by 2. So what will be the complexity of such a thing? Okay, probably chat will help us. Will chat help us? I'm pretty sure you know this function. Sorry? Yeah, logarithm. Yeah, exactly. So this is the logarithm of n. Because you find how many times you should multiply by 2 to get n. So this is exactly logarithm. Okay, great. Good job. Okay, then I again do another algorithm, like some. So I tell less than n, e plus plus. What is the complexity of this algorithm?
What would be like
No.
Square root.
Yeah, it's square root. Exactly. So how many times this operations is going? It is for 1, for 2, for 3, for 4, etc. And when it ends when it gets to n. So it is all square root of n. Okay, good. let us take a little bit more complicated example. Like, let's learn how to multiply two matrices. So we consider squared matrices for us, that it will be easier. So this is the matrix A, this is matrix B, and we want to calculate their so we go from I to n for G to n for K from 1 to n, and then you say Cij plus equal Aik times times B K G. So why does it happen? It is because what's happening, we like how the matrix multiplication works. Okay, let's remember. So we take their ith line, the j column, like we take ith line of the first matrix, we take the j column of the second matrix and multiply this in scalar manner. So we multiply the first by the first here, multiply the second by second here, and add everything together. Okay, so I have for I from 1 to n, for j to 1 to n, I traverse over all their rows, and I traverse over all the columns, and then for each row and column I say, like, I traverse over their length and increment ij position with aik times bkj. So this is exactly, so k is here, k is happening to be here. Okay, what is the complexity of this algorithm? What? I didn't hear. Like, that's.
Okay. N multiply n multiply n.
Okay, great. I sorry, I have a not very good hearing. So like, yeah, exactly. This is all of n cubic. Because you have these inner loops. You go from this loop, you go this, you this, and how much times you like run this separation? You like exactly ijk times, which is all of n cubic. Okay, great. Now let's talk a little bit more complicated example. This is already will be not so trivial as it was previously. So like when you see the algorithm in such a form, you can simply you can calculate their complexity simply by multiplying the number of inner loops, and this will be approximately your complexity. So you just count how many times each loop is running, and you multiply them together. So for example, if there were no this loop, there is no such loop, you will have n squared, simply. If you don't have this loop, then you have again squared, because you have one loop inside another loop, which are like multiplying together. Okay, so when the program is written in such a manner, in such precise manner, it is trivial. But what if I start with recursion? So again, f of n, if n equals to 0, then, I don't know, I print something, print hello. And then I have f of n over 2. what will be the complexity of this function f?
n squared.
Y n squared.
F through each operation and into sorry.
Because let's unroll it, okay? Let's unroll it. So we have if n equals to 0, print hello. Then we start with n over 2. If n over 2 equals to 0, then do this. If n over 4 equals to 0, then do this, and etc. If n divided by 2 in the power of k equals to 0, do something. So how many of these iterations there will be?
It should be logarithmic.
Yeah, it's again logarithmic. It's trivial, right? So you calculate the number of recursive calls and that's it. Okay, great. This is yet trivial, but then I do this. Could you tell me the complexity of such an algorithm? I understand that it really doesn't make sense because it's always print 0, but like how many times it prints 0? Typically, you just have to calculate this number. Any ideas?
Log n squared. Log n squared.
Times n squared? No, it's a little bit simpler. Okay, so how it is solved in general? So you see that you have the recursive function here. Okay, so we have t of n equals to some constant, so this is the constant, plus 2 times t of n over 2. Okay, this is the time complexity of the whole algorithm. We just count this constant and we multiply n over 2 times. It's here. Okay, let's apply this again. C plus 2 times c plus 2 times t n over 4. Okay.
It should be 2 to the nth degree times.
No. Any other ideas? Like, could you try to continue unwrapping this and to calculate what is the complexity of this. Linear? Yeah, exactly. So if you continue to unwrap this, so you have here c plus 2 times c plus 4 times c plus 2 in the power logarithm n times c. And you can see that if you count 1 plus 2 plus 4 plus 3 plus 2 in the power logarithm n, it is simply 2 logarithm n plus 1 times c. But this is no different as 2c times n. So you have the linear. Okay, let's roll it a little bit further and we say f of n over 2 here again.
So it should be a 3 in the degree of logarithm n plus 1.
Yeah, yeah. So this is 3. So it will be 3 in the power logarithm n by 2. This. Because you kind of each iteration you divide by 2, so you know what is the number of layers. Kind of if you draw this in the following manner, so like you have this was f of n, this is f of n over 2, this is f of n over 2. Then again you split to three parts where here are all n over 4. So you can see that you should multiply each 3 times while the height of this tree. The height of this tree is logarithm, as already mentioned, and we have 3 in this power. Okay. Good. So there is a special theorem for that tells how to calculate their complexity of recursive functions. It is said the following, like t of n equals to a times t n over b plus f of n. And it is said if f of n less than equal to n over ab, so we'll proceed like that. We will replace it a little bit further. Oh, sorry. Like this. If fn is smaller than a in the power logarithm, so why I have this a in the power logarithm b of n? It is because here it is exactly like you have in this recursive function, you have logarithm b of n layers because you divide always by b, and you have a here because you have like if you forget about this term, you'll have exactly this number of operations. So then the complexity t of n equals a logarithm b of n. Now, if f of n equals to a log bn, then t of n equals to a log bn times logarithm n. And finally, if f of n is bigger than a logarithm bn, then t of n is just f of n. So like f of n dominates in this. So if it is bigger than, so kind of here dominates this term, here they're kind of equal, and here is dominates this term. Ready? So that is why if we apply it, so we have recursion like this. Oh, sorry. And divided by 2. So we have A here is 3, B here is 2, and we see that the constant C is less than this one. So we fall into this condition, and then the complexity is T of n equals 3 in the power logarithm to n. So this is exactly what we get right now by hands. So suppose that, okay, let me give you a small example. So we could train a little bit on that. So we have again f of n. Then we say, I don't know, for E1n j++, so we have like j something here, j is equals to 1. Here we have j++, and then we call fn over 2, fn over 2. So what will be the complexity of this algorithm? Okay, probably let's start together and then we will finish. Okay, A equal to what? And B equal to what?
2 and 2.
2 and 2, yeah. So like, if you say like B is equals to 2 because we divided by the 2, and A is equals to 2 because we multiply this 2 times. Okay. Okay, what is f of n here?
Well, we do that loop n times, so.
Okay, and what will be here?
It seems like it should be n.
Okay, it is, yeah, it is approximately n, so it is c times n, some constant. We don't know exactly, like, but it is all of n, yeah, exactly. Okay. Yeah, so let it be n. Yeah, like to be more precise, here is like this is not less. This is in of everything. Okay, so what will be equal to this guy in our case?
The right part should be n again.
Yeah, so it is n. So like
It should be the second clause.
it will be the second clause. So all f of n is equals to that. Then the complexity is
N logarithm n.
yeah, n logarithm. Great. So the complexity of this algorithm is all of n logarithm n. Exactly. Okay, so we learn a little bit about complexity. We learn a little bit on how to calculate complexity. So let me, then we will talk about the following. So let us write the simple sorting algorithm. So we will talk about not complexity, but about correctness. Right now, so we finished with complexity, so like you already understand how to calculate the complexity of some algorithms. I want to mention that the complexity kind of give you an intuition whether approximately how fast your algorithm works. So you could say that each computer right now works approximately 10 to the power 8 operations per second. It does more, but like, let's say that we're approximately like this number of operations per second. Okay, so you're like, because typically your practice problems, you should be able to so like you write a program which reads from system input and writes to system output. I hope you know how to do this in your language of choice. And you want to understand what the complexity of the algorithm allows by the conditions, because there will be conditions like n less than equal than 100, n less than equal than 500, and less than equal than 10 to the power of 6. Okay, so if n is approximately 10 to the power of 6, which complexity can fit into this 10 to the power of 8 operations per second? So you want to fit you want to fit your code into their time limit. Okay, do you agree with me that typically like algorithms with O(n) should pass? Because like you approximately do 10 to the power of 6 operations with some constant, you don't know exactly, and it's reasonable. It's reasonable. Like why I'm telling this is because this should be obvious for you that squared solution will not pass here. Because if you take their program with O(n) squared, which is approximately 10 to the power 12 operations per second, which is much larger than 10 to the power of 8. So you cannot fit it into. I give you the intuition of how to understand. So like that you will not try to you will try to solve the problems with their desired complexity, not with their arbitrary complexity. So like on this example, you can see that if n is approximately 10 in the power of 6, your solution should work like O(n) approximately, or O(n) logarithm n. N squared is already too bad. Probably it's even n logarithm squared n. I don't know about your algorithm, but you should understand that n squared shouldn't pass there. So then comes n 10 cubic. Here is typically passes all 10 squared solutions and everything they just faster. For n equals approximately 50 or no, for 5, not 10 to the power of 2, then you could have n cubic. For n 50, you could have O(n) power of 4, and for n approximately like 20, this the expected solution probably 2 to the power of n. This is kind of the cheat list of if you see this condition in the problem, then it should be solved approximately in that running time. So you kind of have to predict how fast your algorithm will work. So like you would think, oh, I know the solution of, I don't know, n times m, but in reality n times n is much bigger than 10 to the power of 8. So like you should come with faster solution. Okay. That's it for complexity. Now let's write our first sorting algorithm. Okay, so here is the algorithm. We just pass from I from 1 to n. Then we go for g from I plus 1 to n. And if ai is bigger than aj, I swap them together. So the first question here. So you are now the experts in complexity. What is the complexity of this algorithm?
N squared.
N squared, great. So like it's already trivial for you to calculate the complexity of such algorithms. That's very good. However, we are left with the question whether it is correct algorithm. So how to prove that this algorithm is correct? So we have an array A, and each time we are passing, so we have this ith position, and we pass it through all the rest of the array, and if it is bigger, then we swap with the parent thing. Can you tell me which value will be after we iterate over all g, like here? So we kind of have a prefix, and we changing I, position of I. Which element will be there at the I place after this loop? This is already a little bit complicated, I understand, so because we are trying to prove already their algorithm, and you haven't done this before, but like, any ideas?
Actually, I don't quite understand the question. Which element in which case? In which sense?
So suppose that okay, let's try it from the start. Okay. No. If it's not clear, then like let's start from the start. So we have one here. Okay. We are on the first iteration of their outer loop. We finish inner loop. Can you tell me what will be in the first place? Which element out of this loop, out of this array, will be on the first place?
First or second depends on what is less.
Not after the first iterations of this term, but like you call already this loop fully, and you go to the second iteration of this loop. So what will be stored in the first cell?
AN plus.
Last? Are you sure? Okay, let us try.
Actually, if we move from the beginning to the end, don't you mean that what should be in the end, the maximum element should be in the end?
No, we have a condition here. We just do not swap arbitrarily. We just like do this by condition. Okay, let's yeah. It seems it's complicated. So let us go through some example together. So we have an array of 5 elements. I don't know, 3, 2, 5, 1, 4. Okay. So we started the first loop. So I is equal to 1, and we iterate over everything else. So we come to the second position. So j is equal to 2. So we compare. If aj is less than ai, we swap them. Okay, so we swap them together. 2, 3. Then we have j equals to 3. We see 2 less than 5. No. Then we will continue. J equals to 3. Okay, so 1 is less than 2, so we swap them and go further. J equals to 4. 4 is bigger than 1, so we do nothing.
No, okay, actually, yes.
So
That's
what?
the minimum.
Yeah, exactly. So at the first place will be the minimum. Okay, great. We know that. Okay, we know that on the first place there will be a minimum of all the elements. Then, suppose we already did I loops. What will be on the after the I loop? What will be stored in this?
Everything greater than this element.
Yeah, this will be the minimum of all the elements on the suffix of this. So how to prove this formally? So let us have an invariant. So all the proofs are typically based on some invariant. So and we will say the following: after I iterations, A1I holds I smallest elements in sorted order. That's just that. And we will prove this by induction. Everybody knows what induction is?
Yeah.
Okay, great. So like, we want to pass from I to I plus 1. So we know that all the elements here are the smallest of everything there. And it's increasing. Then we take, we run our J loop over all the elements, and after this iteration there will be the smallest element out of all of this. Since it is the smallest element, then everything on the right will be bigger than it, bigger than everything on this prefix. And it will be increasing because everything here was the smallest. So like the minimum on the suffix was bigger than here. And that is why we prove that this invariant after I iterations we have like the prefix which is sorted in and which is smallest. So when we finish the algorithm, on the after nth iterations, you will have the sorted prefix of all the elements which is sorted. Okay. Okay, I think this is the introduction lecture, so I think I will stop here. So we can move the second time with a little bit harder material about the sort algorithms, binary search, and ternary search. Are there any questions about what we learned today? So you should come up with understanding on how to calculate complexity, how to prove algorithms. We will prove several algorithms in the future also, and how to what we already. Oh yeah, and we understand how to understand which asymptotics is good for their algorithm in real life applications. So I would encourage everyone to try at least solve one problem of their upcoming contest to understand, like, so that you can ask questions already in advance, because right now I think there are not so many homeworks on you, so you have a little bit time at the beginning, so like that you will understand how to work with their testing system and to understand how it works in general. If there will be any questions, just ask in the chat. I will try to answer as fast as I can. And another thing, there will be no lecture next time. We will have in 1 week through, like over 1 week. Okay. Any more questions right now?
Shall we prove complexity for further homeworks?
Typically, you will prove this like you should prove the complexity for your own. You don't have to, like, because to understand, like, this is exactly the, so you should come up, so you see the problem, I don't know, like, calculate the sum of the elements. And you think, oh, how fast I can solve it? Like, can I solve it in O of n squared? Like, oh yeah, I can solve it in n squared time, but like, let's look on the limitations of that problem. The limitation says like n is 10 to the power of 6. Okay, this means that my algorithm is not very fast, so I have to come up with some approach which is faster. And then, okay, I have 10 to the power of 6, then probably the solution is of n, then probably I have to try to find the linear solution. Then you try to find the linear solution, then you program it, because there is no reason to try to program n squared solution in general, because it will not fit in there into the limits anyway. And then you program the solution for smaller, and you are done, kind of.
So it's not just for the test to pass?
Yeah, it's enough only for the tests to pass, yeah. The first problems that will be given, they're kind of not on their algorithms at all. They're like generic problems where you have to think a little bit. Yeah, that's it. I hope that they will be not very complex. Like the previous group, like like 1 year ago, the group was successful on that. So I hope you will be too. Okay. Thank you everybody for coming. See you in 2 weeks. And if you have any questions, just write to me in the chat. I will try to answer.